Hello learners, welcome back. We are winding up on logic-based testing for now. So what I'm doing in these two modules would be the last two modules of week 6. In this one, we will do logic coverage criteria, summarize it, and I will also talk about a few subtle points that is important to be aware of when it comes to practically using logic coverage criteria. In the next lecture, we will talk about SMT solvers, which we will use briefly when we need to execute test cases and we need to get test cases for logic coverage criteria. So this slide I keep showing because it's a nice ideal recap of all the logic coverage criteria that we've seen and their subsumption. Predicate and clause coverage, test for the whole predicate being true false, each clause being true false. On the left hand side we have active clause coverage criteria, 3 kinds, which exercise each clause in turn to be the major clause and write test requirements for the clause to determine the predicate while imposing restrictions on the minor clauses values. On the right side we have inactive clause coverage criteria, which basically says as a test requirement that the clause chosen as the major clause does not determine the predicate. And then for the sake of completeness, we have all combinations coverage, which is infeasible for all practical purposes, but exists theoretically, where you test for all possible values of the variables for which the predicate can test true or false. So we know that predicates are derived from decision statements. We saw 2 examples of code, type of a triangle and thermostat, where there were many decision statements that had predicates in them. Most predicates in programs have less than 4 clauses, except in rare cases where you have safety critical software, safety critical control software, where the number of clauses can go very high. Most predicates in program have 3-4 clauses in general, 2 clauses also. Many times programs even have only 1 clause. The whole decision statement is one predicate which just has 1 clause without any logical operators. In which case all these coverage criteria that we saw all collapse to just one kind, which is predicate coverage, because the whole predicate is about 1 clause. So all the coverage criteria that talked about various clauses all collapse basically down to predicate coverage. There is another problem to note is that sometimes active clause coverage criteria, they are very useful. They are mandated by several standards, typical practice in testing, but it's difficult to achieve active clause coverage criteria. It might be a bit of work. And so there are also few other issues that we face with logical predicates. And I'll talk about one such common practice issue and a common practice related to logic-based testing. That is the notion of predicate transformation. So as the English meaning of the word says, you have predicates that occur in decision statements, but you would like to transform them or change them. What does it mean to change? It basically means that you rewrite the predicates in the program, especially if they have more than 1 clause. You basically rewrite to ensure that at any point in time, you have only 1 clause in the predicate that you're considering. This means rewriting of the code itself to make sure that the essence of the predicate that had more than 1 clauses is captured by having appropriate nested statements in the code, appropriate decisions in the code. Why do people do predicate transformation? For several different reasons. One important place where logic-based testing is used, where we look at predicates, is when you do testing for security or vulnerability of a particular application. It will come at the ultimate stage when we do system level testing. At the point where we do security testing, if a logical predicate has more than 1 clauses, then typically there could be attacks or compromises on the security where one of the clauses is not exercised, and that is the clause that contains the error. People can bypass or ride without exercising all the clauses. So a simple security vulnerability safeguard is to remove extra clauses in the predicate, is to ensure that you write code such that every decision statement involves only one clause. It's typically considered a standard practice for security vulnerability code, especially when you're writing code that is supposed to be highly secure and vulnerable in an embedded kind of setting. Also, the other reason is while working with cyclomatic complexity. If you remember, we saw cyclomatic complexity in week 4, which is a classical coverage criteria for testing code. One of the requirements, implicit requirements, is that the predicates have to be simple. That is, the predicates have to have one clause, and then we derive the cyclomatic complexity. Similarly, the other reason, as I just told you a little while ago, sometimes if the predicate is too complex, ACC criteria can become expensive for predicates. And one way of overcoming implementing active clause coverage criteria is to rewrite predicates to have one clauses. So predicate transformation is a standard practice that people do for one or more of the reasons that are cited here. So what does predicate transformation do? So predicate transformation, as I told you, involves changing the predicate that you see in a decision statement, specifically a predicate that has more than one clause, rewrite it to have single clauses, which means what? You change the control structure of the program. You add additional nested decision statements that in essence represent the same behavior as that of a predicate. We'll see a couple of examples of what this means. The problem is, in the process of rewriting the control structure of the program, adding a lot more nested decision statements, the program, which was otherwise simple, will start looking very complex. It will be difficult to read. Somebody else who's going to maintain the program later will find it difficult to understand what this is doing. Predicate transformation is usually not recommended, but if you are specifically working with security vulnerability testing or find active clause coverage criteria difficult or are dealing with cyclomatic complexity being low kind of requirements, then predicate transformation becomes very important. So we'll illustrate the issues of predicate transformation through examples. In fact, one of the issues that we will be going to see is one reason that we said predicate transformation is needed is that testers find it difficult to implement ACC criteria. So you rewrite the predicates. But what happens is that in the rewritten new control flow structure, the nested predicates series, predicate coverage on those nested predicates don't correspond to active clause coverage of certain kinds on the full-fledged predicate that was there earlier. So the reason for predicate transformation is a predicate has more than one clause and you are rewriting it by adding extra control flow structure to ensure that the predicate at any point in time has single clauses. So if I have a single clause, then I can consider only predicate coverage for those sequence of predicates. But the problem is the sequence of predicates for which you do predicate coverage doesn't seem to be equivalent to doing active clause coverage on the original predicate. So one of the reasons of overcoming the difficulty of active clause coverage criteria does not exist here. So we'll illustrate all these issues through some examples. So take the small program segment. Always we've looked at program fragments or program statements. So it has an if statement, which is A and B. If this is true, you execute S1. And else you execute S2. So this predicate has a logical connective AND. So it has two clauses A and B. And we've seen this predicate so many times. Test requirement, let's say for correlated active clause coverage for this predicate, which is A and B, we know what it is, right? For making A the major clause once, making B the major clause once, and computing the conditions under which each of these clauses will determine the predicate and populating true-false values. So the test requirement for CACC for predicate A and B would be 3 test cases. A and B evaluating to true, A evaluates to true, B evaluates to false, A evaluates to false, B evaluates to true. If any of you forgot how we got this, go back and refer to earlier slides, earlier lectures on logic coverage criteria. So this is just a recap. Now we don't want to have this A and B, a predicate with 2 clauses. So for some reason, we would want to rewrite this predicate to have only single clauses. So let's try to transform the predicate such that the essence of this condition A and B is fully met. So I transformed this program, which looked very simple, very easy to read, to capture the essence of this A and B, but without using the logical connective as logical connective and. So the transform program removes the logical connective and, but retains the same functionality as that of the original program. And this is how it looks like. So it first says if A is true, then immediately you go and check if B is true. So when you say if A is true and if B is true, then you execute the sequence of statements S1. That's what this also does. If A and B are true, execute the statement S1. Otherwise, A is true, B is false, which means A and B is false, then you execute S2, which is what this also says. Then you execute S2. It could also be the case that A itself is false to start with, then also you execute S2. So we were able to successfully write this code fragment, which had a logical connective with an AND operator, into this kind of code fragment, which didn't have an AND operator here. All the predicates here, 2 of the predicates here, are all single clause predicates. So this was fine. So now let's try to do predicate coverage on this transformed program. I had written CACC criteria for the original program, which was this. I've transformed the original program into this. Now I'm doing predicate coverage on the transformed program. I need 3 test cases. Both have to be true to reach the statement S1, A and B. A has to be true, B has to be false to reach the first occurrence of S2. S2 occurs twice here. It's a replica of the code. And both A and B have to be false, or A has to be false, B can be true to reach the second occurrence of S2. Suppose I choose true, 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 false, and false, false as my 3 parts of the test cases, then we differ from what we had for CACC, which was true, 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 false, and false, true. Whereas predicate coverage here permits me to choose true, 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 false, and one of false, true or false, false. So had I chosen the first one, I would differ from CACC, which means the 2 things, test requirement of CACC on this program is not going to be equivalent to the test requirement of predicate coverage on the transform program. Also, the transform program, if you notice, has 2 replicas of S2, which we couldn't avoid. This means that code is replicated, and this we all know is not a good programming practice. So there are issues like this. In fact, it doesn't stop here. There are more issues. This was a simple predicate. If you had a complex predicate, then your new program that results after the predicate transformation is unrecognizably bad. So I'll illustrate that with another example. So suppose we had the same thing, but with a larger predicate. Instead of A and B, I had A and B or C. So if A and B or C, then you do S1, else you do S2. Is this clear? In this program, we have a predicate with 3 clauses, A, B, and C, connected, A and B connected by an AND operator, C connected by an OR operator. I can rewrite this program to capture the essence of this predicate, but it will result in a very complex control flow structure with several code fragments of S1 and S2 repeating. So I have mentioned the rewritten program here in this slide, and this transform program, if you notice, has the 3 clauses split, and every predicate here has one of the 3 clauses. It doesn't have a single predicate with more than 1 clause. So the first part tests for if A, then if B, then if C, do else S1. Else also you can do S1 because C is connected with A and B with an OR. If this is true, this is false. That is, if B is false, if C holds, then you do S1. If C is false, then you do S2 because B is false, C is false, and then this if condition will evaluate false, then you do S2. Similarly, if else means which means what? If A itself is false, then you check for B and C. If both of them are true, then you could do S1, so on and so forth. It just goes on like this. So what was reading very simple here, the only so-called issue was that this predicate had 3 clauses, but most of the time it's all right. If you try to transform the predicate to have one clause for various requirements, it becomes horrendously complex like this. And with instances of S1 and S2 repeating so many times, if you see S1 repeats 5 times, S2 repeats 2 times. So this code is expensive in its own right. It might avoid a predicate having several clauses, but it's expensive for several other different reasons. So it's ideally not recommended, but do it only when you have to when you're mandated to do it for some security testing and things like that. As you can see, this transform program is much harder to understand than the original one. Of course, I can simplify it, but then it will still be difficult to understand. And the same problem that we had for the earlier example holds here also. Predicate coverage on this transform program is not going to be the same as correlated active clause coverage on the original program. So the thing that I'm trying to tell you is that if you're trying to do it because you're finding ACC criteria difficult to meet, the recommendation is don't do that, because ACC criteria, even if they are difficult to work out, are easier to satisfy, and transform program is more difficult to get, and ACC criteria on the original program don't match predicate coverage on the transform program. So this table I have worked out, not given the working out, but directly given the truth table for A and B or C, which was the predicate that was present in this program here. And CACC test requirements are marked out here. These X's represent the 4 rows which will satisfy CACC, correlated active clause coverage criteria, as a test requirement. Predicate coverage as a test requirement is marked out by these rows. If you see, only 2 of these rows are identical. The rest of the rows are different. So predicate coverage on the transform program is not the same as correlated active clause coverage criteria on the original program. So this was just a small module to tell you that sometimes for some standards meeting certain certification requirements, you might have to work with predicates with one clause. In which case, if you do transformation, then you lose out on the structure of the code. The structure of the code becomes suddenly complex, and active clause coverage criteria on the original program typically don't match predicate coverage criteria on the new program. It's not that we're giving a proof that they never match. Sometimes they could match, but there are enough instances where they don't match. So we have to be careful before we do predicate transformation. So this was one small module that I wanted to do as a part of the summary. The next thing that I want to tell you all about is that you remember for this part of the course, we've been following this textbook on Introduction to Software Testing by Paul Amman and Jeff Offutt from George Mason University. Along with the textbook, they have a website where they give a web application for you all to use for logic coverage based testing. You remember we had done it for graph coverage. The same URL, George Mason University, has a web page for logic coverage criteria. You can input a particular predicate in that and get values for active clause coverage criteria and inactive clause coverage criteria. Try to use it when you're given an exercise. Try to work it out on your own, and you could use this web application to check whether what you have worked out is correct or not, especially for active clause coverage criteria, where there would be several steps to work out to get the test requirements correct. So it's recommended that you use this web application to cross-check your results. That will help you a lot. So I'll end this module by summarizing logic coverage criteria. We saw logical predicates. They were found in code. They were found in requirements. They were found in software artifact models like state machines. For code, you have to work with logical predicate means. You have to solve for reachability. You have to rewrite all the internal variables in the predicates purely in terms of inputs. And then you have to apply the resulting desired coverage criteria on the new predicate that you get that satisfies reachability and has gotten rid of internal variables. If I apply my test requirement for my desired criteria on the transform predicate, I am ready to execute as a test case. To get the test case, I have to pass it to a SAT solver, which is the next module that I'm going to briefly introduce you to. So we'll see that. Logical predicate coverage criteria that comes in requirements or state machines could represent guards on transitions, could be written in English. So there's no problem of reachability or rewriting internal variables because they are in specifications. But the usual problem that you will encounter is that they would be written in English and you will have to translate them into logical form. Make sure the translation is correct and consistent, and then apply logical coverage criteria to design the test cases. So that was a brief summary with a highlight on some issues related to predicate transformation. I'll stop here for now, and the last lecture of week 6, I'll give you a very brief introduction on SAT and SMT solvers. Thank you.